Greetings, and welcome to a journey into the depths of wartime innovation and strategic dominance. Today, we delve into a secret German military installation in Recklin Latz, Mecklenburg, where in 1944, a pivotal discovery was made, one that would challenge all assumptions about Allied air capabilities. Imagine a downed American P-51 Mustang, remarkably intact after being shot near Brandenburg, revealing navigation charts that traced a route over 1,000 miles long from England to Berlin and back. How could such a small, single-engine fighter fly that distance? Could it truly have the range to escort bombers deep into German territory? And what secret American technology allowed these fighters to perform such feats? Something the Germans had never believed possible. But these questions only scratched the surface. Were the Germans right to assume that high-altitude, long-range escort fighters were impossible for the Allies? Could America's industrial might have produced a revolutionary solution, like lightweight, disposable fuel tanks made from paper, that would turn the tide of the air war? And if so, how did these tanks, seemingly so simple, come to be the embodiment of American resourcefulness? Crafted from laminated craft paper, coated with resin, and produced in hundreds of thousands using standard manufacturing techniques? All these elements form a single, staggering puzzle. How did American industrial ingenuity, exemplified by these paper drop tanks, transform the fighter aircraft and the entire air campaign in Europe? The Germans asked themselves, could they counter such resourcefulness? The answer, as the evidence reveals, was no. Because in this war, victory belonged not only to the most advanced technology but to the ability to produce and deploy it on an unprecedented scale. Today, we will trace that journey, from the meticulous examination of captured equipment at Recklin, through the engineering marvels of paper tanks, to the strategic chaos inflicted upon Germany's defenses, and uncover how a simple idea, scaled massively, changed the course of history. The real story begins now. In the spring of 1944, at a strategic military installation in Recklin Latz, situated within Germany's Mecklenburg region, the airfield had become a hub of vital activity for the Luftwaffe's Technical Intelligence Division. This period marked an intense phase of meticulous examination and analysis of captured enemy aircraft, which had assumed unprecedented importance in the ongoing air war. At the heart of this effort stood the renowned Air Probong Stelle Recklin, a cornerstone of Germany's aircraft testing and evaluation infrastructure. Here, teams of skilled engineers, seasoned pilots, and technical experts collaborated tirelessly, striving to uncover every possible advantage that Allied aircraft might possess. Their goal was clear: to understand, counter, and ultimately neutralize the threat posed by the air capabilities of the Allies. The revelations gleaned during this time would prove to be nothing short of transformative, fundamentally reshaping German strategic thinking about air superiority and industrial capacity. A pivotal moment arrived on the 6th of March, when a British railway carried a remarkably intact P-51 Mustang into Recklin's facilities. This aircraft had been recovered from a crash site near Brandenburg 2 days earlier, shortly after being shot down during what was then an unprecedented mission, the initial American fighter escort to Berlin. The downed pilot, unfortunately, did not survive the impact, yet the aircraft itself remained remarkably well preserved. Its condition provided German engineers and technicians with their most comprehensive, detailed example of the aircraft to date, an aircraft that was rapidly changing the face of aerial combat over Germany. Leading the initial examination was Man V. A. Bombeck, a seasoned figure specialized in aircraft development, who would later assume command of Kampfgeschwaden. Under his guidance, the team carefully scrutinized every aspect of the aircraft. Interestingly, The cockpit still contained the navigation charts of the young American pilot, charts which vividly displayed the route from an English airfield at Debden to Berlin and back again. A journey spanning over 1,000 miles in each direction. The technical analysis commenced without delay. German intelligence had been closely monitoring reports of increased American fighter activity far within German-controlled skies, and while their official stance held that single-engine fighters lacked the range to escort bombers to Berlin, these recent events cast doubt on that belief. Historically, the distance from English bases to Berlin was approximately 560 miles one way, a challenge for even the most fuel-efficient fighters, especially considering the need to retain sufficient combat capability. Conventional fighter aircraft, even when equipped with external fuel tanks, had demonstrated an inability to carry enough fuel to complete such a lengthy escort mission without compromising their effectiveness in combat. This assessment was primarily based on prior experiences with aircraft like the P-47 Thunderbolt and the P-38 Lightning, both of which suffered from limited range and were forced to turn back before reaching Berlin during earlier operations. However, the events of early March shattered these long-held assumptions. On the 4th of March, the first combat mission involving P-51 Mustangs, pilots transitioning from P-47s only days earlier, took place. They escorted a modest force of bombers on a mission targeting Berlin. Despite adverse weather conditions and communication difficulties limiting their overall impact, only 32 bombers managed to reach the city's targets. Nonetheless, the mission's significance was unmistakably clear. American single-engine fighters had flown all the way into Berlin, engaged enemy fighters in combat, and successfully returned to England. Just 2 days later, on the 6th of March, an even more striking demonstration of these capabilities occurred. Nearly 750 bombers launched a daylight assault on Berlin, supported by a formidable escort comprising over 150 P-51 Mustangs, as well as P-38 Lightnings and P-47 Thunderbolts. These escort fighters engaged Luftwaffe interceptors directly over the German capital and protected the bomber formations all the way back to their bases in England. Their success was not an isolated incident but an indication that the Germans' previous assumptions about the impossibility of such long-range escort missions were no longer valid. The Americans had effectively solved the formidable escort fighter problem. Their aircraft had crossed a significant threshold, demonstrating strategic range and combat endurance previously thought unattainable for single-engine fighters. This shift in aerial tactics and technology would influence the entire course of the air war, forcing the German Luftwaffe to reconsider its defenses and strategies in the face of an increasingly confident and capable Allied air force. And so, in these pivotal days of March of 1944, the air war was entering a new phase, a phase defined by technological ingenuity and relentless pursuit of aerial dominance. Colonel de Jagdflieger, one of Germany's most accomplished fighter aces with over 100 confirmed victories, had continued flying combat missions during this period despite occupying a significant administrative position. His operational experience was vital, and during these missions, he encountered formations of American P-51 fighters over German territory. Recognizing the significance of these encounters immediately, he understood that they hinted at something extraordinary. In his official combat reports, de Jagdflieger detailed an alarming observation: the American fighters were operating at their peak combat readiness over Berlin, engaging with relentless aggression. They showed no signs of conserving fuel or avoiding extended dogfights, behaviors that were inconsistent with conventional intelligence assessments. Instead of flying within their known range limits, these P-51s appeared to have a significant reserve of fuel, enabling them to sustain prolonged engagements and still find a way to return home. This discrepancy stood in stark contrast to the earlier intelligence that the Luftwaffe had relied upon regarding American fighter capabilities. The reports from Gallen and his team highlighted the P-51's remarkable performance at high altitudes, where it outperformed both the Messerschmitt Bf 109 and the Focke-Wulf FW 190 in terms of speed and agility above 20,000 feet. These insights prompted German engineers and technical teams to investigate how the Mustang achieved such impressive range and endurance. The primary focus of their examination was the aircraft's internal fuel capacity. They measured the fuel tanks integrated into the P-51B variant, discovering that it housed two wing tanks, each capable of holding 92 gallons of aviation fuel, totaling 184 gallons in the wings alone. Additionally, there was a fuselage-mounted tank, situated just behind the cockpit, with a capacity of 85 gallons. This fuselage tank was a relatively recent modification introduced during the P-51B's production run, purposefully added to extend the aircraft's operational range. When combining all sources, the total internal fuel capacity reached a staggering 269 gallons. The aircraft was powered by a Packard-built Merlin engine, a licensed version of the legendary Rolls-Royce Merlin, which had significantly enhanced the Mustang's high-altitude performance. Fuel consumption rates varied depending on the engine's power settings. At economy cruise, the engine burned roughly 60 gallons of fuel per hour, whereas at standard cruise power, the rate increased to around 75 gallons per hour. German engineers used these figures to perform range calculations. Assuming an internal fuel capacity of 269 gallons and a consumption rate of approximately 70 gallons per hour during normal cruise, the P-51B could theoretically sustain flight for about 3.8 hours. Given its cruising speed of roughly 300 miles per hour, this translated to a maximum operational range of approximately 1,140 miles. Remarkably, this range was just about enough for the P-51 to fly from English bases over the English Channel to Berlin and back, but it left no margin for extended combat or emergency reserves. However, actual combat reports painted a different picture. Despite the limited range suggested by calculations, these American fighters were observed engaging in prolonged dogfights over Berlin, sometimes lasting 15 to 20 minutes, before breaking off and returning safely to base. The level of fuel consumption during these intense battles was reportedly exceeding 100 gallons per hour, especially when pilots used full power settings during combat. Any such aggressive flying should have depleted their fuel reserves to the point of making return impossible. The calculations based solely on internal fuel capacity and normal consumption rates failed to satisfactorily explain what the German pilots were witnessing firsthand in combat. To understand the discrepancy, the technical staff conducted a more detailed examination of the aircraft's wing structure. Their attention was drawn to the standardized hard points under each wing, which were designed to carry external stores. These hard points included provisions for external fuel tanks, with dedicated fuel line connections clearly visible, indicating these were not mere placeholders but integral components intended specifically for external fuel tanks. Drop tanks, as they were called, were not an entirely new concept for fighter aircraft. German fighters had utilized external fuel tanks since the early days of their combat operations, aiming to extend their range and endurance. Recognizing that the P-51s might be carrying additional external tanks, the personnel began to consider that these tanks could significantly increase the aircraft's fuel capacity and thereby its operational endurance far beyond what internal tanks alone could provide. This realization pointed toward a possible explanation for the observed combat endurance. If the American fighters were deploying external fuel tanks during their missions, something that wasn't always apparent at first glance, they could have accessed substantially larger amounts of fuel. The external tanks, likely drop tanks, would be jettisoned after they were emptied, allowing the aircraft to return with the internal fuel reserves. This would account for the discrepancies between the theoretical range calculations based on internal fuel capacity and the actual endurance observed during combat situations over Berlin, where fighters seemed capable of engaging in extended, energy-consuming dogfights without immediate regard for fuel constraints. Of Britain, the use of drop tanks by aircraft such as the Bf-109 and Fw-190 was a common practice during the conflict. The Bf-109 was capable of carrying a drop tank with a capacity of approximately 300 liters, while the Fw-190 often employed them for extended-range missions, enabling aircraft to undertake longer flights without refueling. These external fuel tanks served a critical purpose by allowing planes to carry additional fuel beyond their internal tanks. Once the mission's critical phase was approaching, they could be jettisoned to reduce weight and aerodynamic drag, thereby restoring maximum maneuverability and speed for combat engagements. In the broader context of military aviation, such drop tanks were standard across many air forces engaged in the war. The focus, particularly on the Allied side, was not merely on whether they employed these auxiliary fuel tanks but centered instead on understanding their capacity, production capabilities, and how supply chains managed to sustain the high operational tempo of their air campaigns. This curiosity prompted immediate efforts to locate and analyze American drop tanks from the recent missions conducted in March. Allied intelligence officers quickly mobilized to investigate potential locations where tanks might have been jettisoned. They mapped out likely points where the tanks could be found, based on the reported engagement zones provided by Luftwaffe pilots who had experienced aerial battles firsthand. These tanks were typically released when enemy fighters appeared, as carrying external stores adversely affected an aircraft's ability to maneuver and increased its drag, making it more vulnerable but necessary for extending range or fuel endurance. Teams consisting of Wehrmacht personnel and Hitler Youth volunteers were dispatched to search the countryside northeast of Berlin, systematically exploring fields and forests for debris from the air battles. Their efforts were swift. Within 3 days, they recovered several fragments scattered across the region. Most of these pieces were damaged or crushed upon impact through either the force of falling or subsequent environmental effects, which made them fragmentary and challenging to analyze. However, among the recovered debris, 2 intact drop tanks arrived at the Luftwaffe's testing and analysis facilities in Vlan. These tanks had landed in relatively soft soil or winter wheat fields, which cushioned their fall, preserving their structural integrity. This preservation became a breakthrough for German engineers seeking to understand the construction and capabilities of the American tanks. The analysis of these tanks shed new light on American manufacturing techniques. They were cylindrical in shape, measuring approximately 108 inches in length with a diameter of about 22 inches at the widest point. From capacity calculations based on their dimensions, it was estimated that each tank held roughly 108 U.S. gallons, equivalent to around 400 liters. When considering the use of 2 such tanks on a single aircraft, the total additional fuel capacity amounted to approximately 216 gallons, significantly boosting the aircraft's endurance. This increase in fuel capacity meant that the P-51 Mustang could now carry a total of around 485 gallons, allowing for extended flight durations. At cruising power settings, this load translated into an operational endurance of roughly 6 hours and 42 minutes, providing a range exceeding 2,000 miles. Such range was more than ample for the Berlin mission, offering substantial reserves for escort and contingency maneuvers. Understanding the mathematics of the fuel capacity now seemed straightforward, but what truly captivated the German engineers was not just the volume of fuel these tanks could hold, but rather their innovative construction. The material used for these external tanks was unlike anything they had encountered before. Running a hand along the smooth exterior surface revealed a texture that did not resemble aluminum or steel, the typical materials used in aircraft construction. The metallic sheen, coated by silver paint, could not conceal the fundamental nature of what lay beneath. When the engineers carefully scraped away a small section of the paint near the tail cone, they discovered a complex, multi-layered structure beneath. It consisted of multiple layers of heavy paper, each approximately half a millimeter thick, carefully compressed and laminated together with an adhesive that was resilient and durable. This construction was both sophisticated and deliberate. The nose cone and tail cone of the tanks were formed from overlapping pieces of this specially designed paper material, pressed into shape much like papier-mâché. These overlapping sections created a scalloped appearance along the surface, with each ridge indicating the boundary between individual layers. The center section of the tank was a seamless wrap of this material, meticulously rolled and pressed around a cylindrical form in continuous, unbroken layers. The tank's fuel fittings were crafted from brass, expertly machined and sealed to prevent any leaks. When examined closely, it became clear that the entire construction was a testament to ingenuity, employing unconventional materials to achieve a lightweight yet durable external fuel tank. Peering through the various layers and inspecting the fittings, engineers gained valuable insight into the innovative manufacturing techniques employed by the Americans, revealing a level of resourcefulness that could potentially influence German design approaches in future aircraft and fuel storage technologies. The filler cap, when examined closely, revealed an interior surface coated with a substance that appeared to be a cellulose-based lacquer famously designed to withstand the corrosive properties of aviation gasoline. This layer was not merely a coating but a carefully engineered protective barrier, crucial for maintaining the integrity of the tank in the harsh conditions of wartime aviation. To understand the full extent of this innovation, German materials specialists were summoned, brought in to scrutinize the construction of these unconventional fuel tanks with meticulous precision. Their investigation uncovered that the main body of the tank was crafted from craft paper, an industrial-grade material produced through a chemical pulping process designed to generate fibers of extraordinary strength and durability. This particular paper was well known in manufacturing circles, commonly employed in the production of heavy-duty shipping containers and industrial packaging, precisely because of its resilience and capacity to withstand rough handling. The adhesive used to laminate the layers of this paper was identified as a form of phenol formaldehyde resin, more specifically, a resorcinol formaldehyde adhesive, a type of thermosetting polymer renowned for creating bonds that are significantly stronger than the paper itself once cured with heat. In constructing the tanks, a minimum of 12 separate layers of this specially treated paper were carefully stacked, each layer meticulously oriented to maximize structural strength in multiple directions. This process resulted in a composite material that, despite its unconventional nature, was remarkably sturdy. Moreover, inside the tank, anti-slush baffles, crafted from wood, were installed to prevent unsteady fuel surges during rapid maneuvers, ensuring stability and safety in flight. It was evident that the entire manufacturing process for these paper tanks was highly standardized, optimized for rapid mass production on a large scale. One of the most striking features was the weight comparison. An empty paper tank weighed roughly 80 pounds, whereas a metal tank of similar capacity would typically weigh between 65 and 75 pounds. While the paper-based construction was not dramatically lighter than its metal counterparts, it offered other compelling advantages that could not be ignored. For the technical staff at VLAN, the implications of this discovery were immediately apparent. The Americans were manufacturing fuel tanks from materials that did not fall under the category of strategic metals, such as aluminum or steel, that were increasingly scarce and difficult to obtain during wartime. Instead, they relied on readily available, non-strategic resources like paper and wood-based resins. The manufacturing process itself did not require sophisticated metalworking tools, specialized welding equipment, or highly skilled metalworkers. Standard manufacturing facilities, such as paper mills or industrial packaging plants, could be adapted with relatively simple modifications. Given that the United States boasted hundreds of such factories, the potential scale of production was staggering. If even a small fraction of American paper production capacity was diverted to manufacturing these drop tanks, the output could easily reach thousands of units every week. The tanks themselves were devoid of serial numbers or manufacturer marks, appearing as generic, mass-produced commodity items designed to be expendable. Their simplicity and uniformity underscored their role as disposable supplies rather than prideful pieces of engineering. In light of this, intelligence officials set about evaluating the capacity of the American paper industry. Prior to the war, the United States produced approximately 12 million tons of paper each year, with this figure having increased significantly during wartime mobilization efforts. Converting just 1% of this vast capacity into production for drop tanks could theoretically yield over 100,000 tanks per month, an output vastly exceeding what would be necessary for operations involving aircraft like the P-51 Mustang. In reality, the bottleneck would not be the materials but rather the availability of manufacturing machinery and labor to assemble such quantities. However, this posed no insurmountable obstacle, as the manufacturing of these tanks relied on semi-skilled workers who could be trained quickly, and existing equipment that could be adapted with minimal effort. The tank's design, simplicity, and the ease of mass production reflected industrial efficiency and resourcefulness on an unprecedented scale, an approach that German planners found difficult to fully grasp or counter. Further detailed analysis uncovered additional insights into the design and operational use of these paper tanks. It became clear that they were intended strictly as single-use items, meant to be deployed and discarded after a single mission or limited operational period, further emphasizing their role as a cost-effective wartime resource rather than durable, reusable components. During World War II, a fascinating innovation emerged in the realm of aerial fuel storage, fundamentally altering the logistics and operational strategies of both Allied and Axis forces. This innovation was the development of paper drop tanks, an ingenious solution to the urgent need for lightweight, easily deployable fuel containers that could be produced rapidly and disposed of after use, thereby simplifying supply lines and maintenance procedures. The core component of these tanks was a specially treated resin adhesive, which, once cured, provided remarkably strong bonds essential for withstanding the rigors of flight. However, this adhesive had its limitations. Over time and with prolonged exposure to aviation gasoline, it gradually disintegrated. As a result, the tanks were designed for short-term use, with the understanding that they would be filled just before a mission and discarded shortly thereafter. Interrogations of captured American aircrew and intelligence reports confirmed that these paper tanks had to be filled immediately prior to takeoff. Storing them filled for several hours led to leaks and failure. Nonetheless, This constraint was not considered a significant obstacle, as aircraft were typically fueled during their pre-flight preparations, ensuring the tanks were ready when needed. These tanks were intended for single use only, an approach that, rather than complicate logistics, actually streamlined it. The design eliminated the necessity for recovering, cleaning, inspecting, or maintaining the tanks after each mission. Once jettisoned, they could be simply discarded, reducing the logistical burden on ground crews and enabling rapid turnaround times between flights. This disposable nature was a deliberate feature, not a flaw, optimized for operational efficiency. Color coding played a practical role in operational efficiency as well. The British-designed paper drop tanks were painted in a bright silver hue, a choice that served multiple purposes. Firstly, the reflective surface helped to deflect solar heat, thereby reducing evaporation of the fuel and lowering vapor pressure issues during high-altitude flights. Secondly, the color differentiation allowed ground crews to instantly identify the type of tanks, silver for paper tanks and gray for the metal tanks used by American forces, facilitating faster and more accurate fueling procedures. Every element of the paper drop tank's design was a testament to systematic engineering aimed at mass production and field readiness. By late March of the year 1944, intelligence reports had successfully traced the origin of these paper tanks back to British developmental efforts. The British Ministry of Aircraft Production had originally commissioned the creation of impregnated paper fuel tanks in the year 1943 as part of a strategic resource conservation initiative, particularly aimed at reducing the reliance on expensive and limited aluminum supplies. The Bowater Scott Corporation, leveraging its expertise in paper manufacturing, spearheaded the development process, creating a production method that enabled rapid, large-scale manufacture. These tanks entered operational service with Royal Air Force fighter squadrons in late 1943, quickly proving their value in combat scenarios. American forces, recognizing the efficiency and practicality of the British design, swiftly adopted it. Multiple manufacturers across both Britain and the United States produced the tanks, integrating them into the arsenal of United States Army Air Force's fighter groups. This widespread adoption underscored how resource scarcity, initially the driving force behind the design, had catalyzed an industrial shift of enormous scale, with American industry harnessing its vast capacity to produce these tanks in unprecedented numbers. The broader implications of this technological shift extended well beyond merely fuel storage. German technical analysts, recognizing the significance of this innovation, embarked on meticulous evaluations of captured American military equipment. Their systematic review revealed a crucial insight. While German technical standards often surpassed American counterparts in specific areas, such as optics, small arms design, or armor metallurgy, American equipment was generally superior in production quality, reliability, and availability. American components were designed with an emphasis on manufacturability rather than perfection. They were engineered from the outset for mass production by semi-skilled workers, utilizing standardized tooling and interchangeable parts that required no time-consuming hand-fitting. Assembly line techniques, pioneered in American factories, dramatically reduced production times while increasing output, enabling vast quantities of equipment to be generated swiftly and efficiently. This manufacturing philosophy contrasted sharply with German practices, which prioritized exquisite craftsmanship and technological refinement. While German optical systems might have offered superior clarity and precision, American production methods resulted in equipment that was more standardized, more reliable, and more widely available. The systematic approach to mass production underscored a fundamental strategic difference. Americans favored a pragmatic, results-oriented manufacturing model that prioritized ease of assembly, cost-effectiveness, and high-volume output, whereas Germans often pursued technological perfection at the expense of manufacturing speed and scale. Ultimately, this industrial strategy contributed significantly to the Allies' military advantage, allowing them to equip vast numbers of aircraft, tanks, and other equipment with consistent quality and reliability. The emphasis on producing components designed for rapid, large-scale manufacturing transformed the logistics of war, enabling Allied forces to sustain prolonged campaigns and adapt swiftly to changing battlefield conditions. This paradigm shift in industrial capability proved to be one of the most influential aspects of the war effort, shaping the outcome of the conflict and setting new standards for military production in the decades that followed. During the wartime era, the Germans were renowned for their meticulous craftsmanship and exceptional precision when it came to manufacturing military equipment. Their weapons and equipment often stood out as masterpieces of engineering. Each tank, aircraft engine, or piece of artillery was a testament to the skill of highly trained artisans and technicians. German tanks and aircraft engines exemplified the pinnacle of detailed engineering, with each component carefully hand-fitted to ensure maximum performance and reliability. However, this focus on craftsmanship came with significant limitations. Producing such highly specialized and precisely crafted equipment demanded not only highly skilled labor but also specialized tools and considerable time to produce each unit. As a result, the pace of manufacturing was constrained by the availability of master craftsmen and the capacity of precision manufacturing facilities, which could only produce a limited number of units within a given time frame. In contrast, the Americans adopted a different approach in industrial warfare. Instead of striving for the highest possible quality in each individual item, they prioritized mass production of sufficiently effective equipment, relying on sheer volume to achieve dominance. Although American-made equipment might not have matched the German standards for craftsmanship or technological sophistication on a per-unit basis, the overwhelming scale of American production proved to be a decisive advantage on the battlefield. This strategic difference was particularly evident in the case of the P-51 Mustang fighter aircraft. The story of the P-51 Mustang's development and production vividly illustrates this overarching principle. North American Aviation was tasked with designing the original Mustang prototype in response to a British requirement issued in 1940. Remarkably, the company completed the initial prototype, designated NA-73X, just 117 days after signing the contract. A record-breaking achievement in aviation history that underscored the rapid pace of American aircraft development. The prototype made its maiden flight on October 26, 1940, marking the beginning of a production effort that would soon become a cornerstone of Allied air power. By the year of 1944, North American had established production lines at two major facilities to meet the soaring demand for Mustangs. The plant, located in Englewood, California, ramped up to an average output of approximately 364 aircraft per month during peak production periods. Meanwhile, the Dallas facility contributed additional assembly capacity, enabling the combined monthly production to reach around 574 aircraft throughout the year. The production rate increased steadily, culminating in a peak monthly output of nearly 956 aircraft in January of 1945. Each P-51 Mustang was an intricate assembly of roughly 15,000 individual parts, manufactured by hundreds of subcontractors spread across the United States. The engines powering these fighters, specifically the Merlin engines built by Packard, were produced in Detroit at rates surpassing 300 units per month. final assembly of a single P-51D required about 22,000 man-hours of skilled labor. Yet, thanks to a highly efficient production line system, completed aircraft would roll out of the factory every few hours. At the height of efficiency, a new Mustang was completed approximately once every 2 hours, a staggering feat of industrial organization and logistical coordination. This enormous scale of American production, coupled with its high efficiency, far exceeded the capabilities of German aircraft manufacturing. By early 1944, German aircraft producers like Messerschmitt and Focke-Wulf managed to produce around 600 fighters per month, despite operating under emergency priority programs and even utilizing forced labor in some cases. The resource implications of American industrial prowess were equally impressive, particularly in terms of aluminum, a vital material for aircraft manufacturing. In 1944, the United States produced approximately 1,250,000 tons of aluminum annually, a volume equivalent to about 2,500,000,000 pounds. This was a colossal increase from the pre-war American aluminum production of approximately 164,000 tons in 1939. Meanwhile, Germany's aluminum production capacity, peaking around 250,000 tons annually, was suffering from the effects of strategic bombing campaigns targeting their factories and the loss of critical bauxite sources. The Americans, possessing roughly 10 times Germany's aluminum capacity, could sustain a much larger aircraft manufacturing effort. Interestingly, in the case of drop tanks, fuel tanks used to extend the range of Allied fighters, the decision to produce these from paper rather than metal was not driven by aluminum shortages, as the United States had enough aluminum to manufacture every drop tank in metal if needed. Instead, paper was chosen because it was significantly cheaper and required less critical material, further exemplifying American resourcefulness and prioritization of mass production over perfection. In summary, the United States' ability to produce vast quantities of adequate, functional equipment, enabled by advanced industrial systems and abundant resources, ultimately overwhelmed the Germans' more craft-oriented, precision-focused manufacturing approach. This industrial strategy, characterized by high volume, rapid output, proved to be a decisive factor in the outcome of the war. The development of specialized manufacturing equipment allowed for the rapid production of aircraft components, freeing up valuable aluminum supplies for other critical uses across the war effort. This innovation also meant that aircraft could be built more swiftly and with less need for highly skilled labor, streamlining the entire production process. Such advancements reflected a strategic shift. These were deliberate measures aimed at increasing efficiency and output, not signs of desperation. The significance of these technological and industrial improvements resonated deeply within the Luftwaffe's technical and operational communities. The revelation of the drop tank's capabilities became a potent symbol of American industrial prowess and a stark illustration of the vast disparity in resources between the two sides. It wasn't merely a tactical tool. It embodied the broader industrial and logistical advantages that the Allies had harnessed. Captured examples of these drop tanks were displayed prominently at technical briefings, serving as visual aids to inform Luftwaffe personnel about the new American technological edge. Pilots, especially those transitioning from training to active fighter units, were shown these tanks and prompted to consider their tactical implications. The message was unambiguous. American fighters now had the range and endurance to escort bombers deep into Germany, fundamentally altering the strategic landscape of aerial combat. The traditional defensive posture, waiting for Allied fighters to run low on fuel and turn back, was rendered obsolete. German fighters would now have to engage and combat the escorts to reach the bombers, a task that would often result in considerable losses. These engagements would come at a steep cost: aircraft and experienced pilots, losses that Germany could ill afford to sustain. Throughout the spring of 1944, General Galland consistently provided detailed operational assessments to senior Luftwaffe leadership. He emphasized that the P-51 Mustang had become superior to German fighters at elevations above 20,000 feet. Its increased speed, especially at high altitude, surpassed that of the Bf 109, while its maneuverability outperformed the Focke-Wulf 190. With the added advantage of extended range through drop tanks, the Mustang could accompany bombers on their entire mission profile, from takeoff to landing. This technological edge meant that German fighters could no longer threaten unescorted bomber formations without risking significant losses. Once Allied fighters had turned back, their escorts could challenge the Luftwaffe fighters with impunity, knowing the Germans now faced an increasingly deadly and well-supported enemy. Every interception became a costly encounter, requiring German pilots to fight through formidable fighter screens with mounting risks. The toll on Luftwaffe fighters became increasingly severe. In January of 1944, German losses amounted to approximately 90 fighters, while their claims for destroyed Allied aircraft stood at roughly 150. By February, losses had climbed to about 160 fighters against approximately 230 Allied aircraft destroyed. The pattern was unmistakable and unsustainable. German losses were escalating faster than they could be replaced. The summer of 1944 starkly demonstrated the full impact of American escort capabilities. Nearly every day, the 8th Air Force conducted deep penetration raids into Germany whenever weather conditions permitted. The Mustang's extended operational range allowed it to provide continuous escort from England all the way to distant German targets and back, shielding the bombers from enemy fighters. Meanwhile, Luftwaffe fighter losses soared catastrophically. In June of that year, approximately 350 German single-engine fighters were lost in defense of the Reich. The following month, losses exceeded 350, terrain losses that represented a rate of attrition surpassing 31% for the month. August saw similar figures, with attrition rates reaching 36%, leading to a rapid depletion of experienced pilots. Many of these pilots were killed before they could accumulate enough flight hours, often little more than 150 hours of combat experience, compared to American pilots, who typically had 300 hours or more. The gap in operational experience was further widened by the influx of replacement pilots, many of whom had completed only about 30 hours of flight training on the specific aircraft type before being thrown into combat. This stark disparity in training, coupled with the relentless pressure of numerically inferior forces and the constant threat posed by the P-51 escorts, made daylight operations over Germany increasingly perilous for the Luftwaffe. The combination of technological, numerical, and experiential disadvantages was steadily crippling Germany's capacity to contest the skies effectively. Throughout this period, Dr. Galland persistently submitted detailed assessments to Hitler and the senior leadership of the Wehrmacht, offering candid evaluations of Germany's deteriorating war situation. By September of 1944, his reports painted a stark and unambiguous picture of the state of affairs, emphasizing the impossible odds faced by the German Luftwaffe. He bluntly stated that the Air Force was effectively incapable of winning the air war. Germany was critically short of vital resources, fuel, aircraft, and well-trained pilots, making it impossible to challenge the overwhelming air superiority of the Allies. The Americans, with their vast industrial capacity, could replace aircraft, pilots, and losses at a pace that far outstripped Germany's ability to inflict damage or recover from setbacks. This disparity was more than just a numbers game. It reflected a fundamental imbalance in economic and industrial strength. While the Allies could sustain their war effort through relentless production and resource reallocation, Germany's own industrial capacity was stretched to its limits and unable to keep up with wartime demands. The only remaining strategic option, therefore, was to conserve whatever resources remained, shifting focus toward the defense of vital targets, and to hold out hope that a political solution or surrender might happen before complete military collapse. Evidence of these efforts was visible in the continuous fall of paper drop tanks, which persisted across Germany from late 1944 into the early months of 1945. German civilians quickly learned to recognize the distinctive cylindrical shapes of these drop tanks, which often lay abandoned in fields and forests. Early reports sometimes led to panic, as many believed these objects to be unexploded bombs. Only later did military authorities clarify their purpose, explaining that these were harmless fuel tanks, not explosive devices. Civil defense authorities issued instructions to the population, emphasizing that the falling silver cylinders from Allied aircraft were empty fuel containers, harmless and not dangerous, intended to reassure and reduce panic among civilians. The psychological impact of the aerial drop was profound and well documented in morale reports. Seeing enemy aircraft so numerous that their contrails crisscrossed the sky, casually discarding these fuel tanks, served as a stark visual reminder of the Allies' vast resources. It reinforced the perception that the Allies could afford to waste supplies while Germany was fighting desperately to conserve every last liter of fuel and every ounce of aluminum. This visible disparity in resource availability contributed to a sense of helplessness and despair among the German civilian population and military strategists alike. Meanwhile, technical intelligence teams continued analyzing captured American equipment throughout the year 1944. Their focus gradually shifted from merely understanding the capabilities of Allied technology to quantifying the scale of industrial disparity. The question arose: could Germany manufacture similar paper drop tanks? Technically, the answer was yes. German industry had the capacity to produce suitable resins using their chemical industry, and their paper mills could manufacture kraft paper capable of serving as a fuel tank shell. The manufacturing process itself was relatively straightforward, involving no particularly advanced technology. Despite this, the practical realities made such production impossible. Germany's chemical industry was operating at maximum capacity, producing crucial items like synthetic rubber, explosives, and other vital materials necessary for the war effort. Resins for non-essential purposes, such as fuel tanks, could not be prioritized without compromising essential manufacturing. Likewise, the German paper industry was fully committed to producing maps, military documents, and packaging materials vital for logistical and operational needs. Most critically, there was no operational requirement or strategic doctrine calling for extended-range drop tanks, especially as fuel shortages by late 1944 had grounded large segments of the Luftwaffe. With fuel increasingly scarce, pilot training was drastically curtailed, and operational sorties became limited primarily by fuel availability rather than aircraft readiness. Building and deploying drop tanks to extend aircraft range became a moot point when there was barely enough fuel for defensive operations or the day-to-day missions of the remaining aircraft. The irony was particularly bitter for German planners. While the Americans had devised solutions to their fighter range problems by developing paper fuel tanks, an innovative and cost-effective method, by the same period, German fighters had been grounded due to fuel shortages. The contrasting industrial bases and strategic realities resulted in vastly different outcomes, with the Americans outpacing Germany in virtually every resource and technological aspect. In summary, the American war effort benefited from unparalleled industrial strength, allowing them to develop, produce, and deploy technologies such as paper fuel tanks that addressed critical operational challenges. Meanwhile, Germany's industrial capacity was overwhelmed, and its strategic options severely limited, leading to a desperate reliance on resource conservation and makeshift solutions. The disparity between the two sides grew ever more pronounced, highlighting the fundamental differences in their economic and industrial structures, differences that ultimately determined the course and outcome of the conflict. ILITY became painfully evident to all who visited the exhibition, revealing the stark contrast in industrial strength and technological prowess between the two sides. This display underscored a fundamental truth: that the Axis powers, particularly Germany, faced insurmountable logistical and industrial obstacles in attempting to match the relentless, large-scale production capabilities of the Allies. By the time January of the year 1945 arrived, the outcome of the conflict was essentially sealed beyond any doubt. Soviet forces had advanced relentlessly, drawing dangerously close to the Uda River, a mere 50 miles from Berlin itself, signaling that the final battle for the German capital was imminent. Meanwhile, in the West, the Allied forces had rebounded from the setbacks of the Ardennes offensive and were now pushing steadily toward the Rhine River. Despite the Luftwaffe's efforts to resist, their ability to mount sustained aerial opposition had become severely limited, constrained largely by dwindling fuel supplies and the increasing losses of experienced pilots. During these final months of the war, the systematic analysis of American military equipment persisted, particularly at Recklin, but by then, such technical studies had taken on a mainly academic nature. Their findings were meticulously recorded for posterity, yet they could no longer influence the course of the conflict. The most comprehensive evaluation of the P-51 Mustang and its innovative drop tanks was completed in late January, providing a detailed account of its technical capabilities, construction techniques, and operational advantages. This report scrutinized everything from the materials used in the non-strategic paper drop tanks to production estimates and the strategic implications of their widespread deployment. The conclusion drawn was unequivocal. The P-51 Mustang, equipped with these lightweight, expendable paper drop tanks made from readily available materials, had transformed the strategic landscape of the air war. It had essentially rendered Germany's heartland indefensible against American daylight bombing campaigns, which could now reach deep into the German interior with relative ease and sustained operation. Germany, despite its wartime efforts, lacked the industrial capacity to produce fighters on a scale necessary to challenge the Allied air dominance. Its fuel reserves were insufficient to sustain continuous, large-scale combat operations, and its trained pilots were being lost at an alarming rate, losses that could not be quickly replenished given the depleted state of German military aviation training programs. These grim realities were documented and archived in the Reich Air Ministry during late January 1945, but whether they reached the attention of top leadership remains uncertain. By that point, the Germans had come to understand, through both strategic analysis and battlefield observation, that their aerial adversaries possessed capabilities far superior in quantity, quality, and industrial backing. The Luftwaffe, which had once dominated European skies in the year 1940, was now reduced to sporadic, desperate sorties. These last-ditch efforts were characterized by frantic, limited operations aimed more at delaying the inevitable than changing the strategic calculus. The fuel shortages and increasing attrition had made sustained resistance impossible, leaving the German Air Force largely a shadow of its former self. Meanwhile, American fighters cruised unchallenged over Germany, conducting attacks on targets of opportunity, providing escort for bombers, and establishing uncontested air superiority. Each successful mission, each paper drop tank released from an American aircraft, served as a stark reminder of the vast industrial gap between the two nations. These lightweight tanks, made from non-strategic, easily obtainable materials, symbolized the technological ingenuity that had turned the tide of the aerial war decisively in favor of the Allies. In June of 1944, an exhibition held at Recklin displayed captured Allied aircraft, including multiple examples of the P-51 Mustang, alongside B-17 Flying Fortress and B-24 Liberator bombers, P-38 Lightning fighters, Lancaster bombers, Mosquito fighters, Typhoon fighters, and various models of Spitfire. Thousands of Luftwaffe pilots and ground crew visited the exhibit, some for the first time seeing enemy equipment firsthand. Prominently displayed were the paper drop tanks, accompanied by detailed technical diagrams that explained their construction, materials, and the strategic advantages they conferred. This exhibition served a dual purpose. It was an educational experience that showcased the technological advancements of the Allies and a sobering reality check that underscored the industrial disparity that had decided the outcome of the air campaign. The Germans could see the quality, standardization, and sheer scale of Allied production, which reinforced the bleak understanding that their own industrial efforts simply could not keep pace. The overwhelming force of Allied industrial mobilization was plastered across every facet of the war, from the quality of aircraft to the logistics supporting their sustained air campaigns, leaving little doubt about the eventual outcome that was now clearly on the horizon. The concept of practical experimentation was vividly brought to life through tangible, physical examples of the equipment that pilots faced on the front lines each day in combat situations. One notable example was the KF Kaschwada 200, a specialized unit within the Luftwaffe responsible for executing high-stakes operations, which included the daring task of flying captured Allied aircraft, notably the famous P-51 Mustangs, throughout the year of 1944. These aircraft weren't just trophies. They served as vital tools for England's adversaries to evaluate and understand the capabilities of the enemy's top-tier fighters. Throughout that period, these Allied fighters, especially the P-51s, became the subject of extensive testing, with Luftwaffe test pilots taking to the skies in their evaluation flights. Their first-hand experience provided invaluable insights into what made the Mustang an exceptional fighter aircraft. The pilots' reports consistently highlighted several key features: an outstanding cockpit visibility, which was particularly notable in the later P-51D model fitted with a distinctive bubble canopy, greatly enhancing pilot awareness and safety during combat maneuvers. They observed that the aircraft was remarkably stable once in flight, responding accurately and predictably to pilot inputs, which made it not only a formidable opponent but also easier to handle under combat stress. Furthermore, the Mustang's performance at high altitudes was noted as being superior, allowing it to maintain effectiveness in the challenging environments where many dogfights took place. Its power plant, the Merlin engine, delivered smooth, reliable performance across the aircraft's entire operational envelope, providing confidence and control to the pilot in both routine and tense situations. Perhaps most impressive was the Mustang's impressive range and endurance, which were extraordinary for a single-engine fighter of that era. With full internal fuel tanks supplemented by additional drop tanks, the aircraft could stay airborne for more than 6 hours, a duration that surpassed what most German single-engine fighters could manage, even with external tanks attached. This remarkable endurance meant the Mustang could conduct long-range patrols and escort missions, effectively covering vast areas without the need for frequent refueling. The technical insights gained from these evaluations at the Recklin facility played a significant role in shaping German defensive tactics during the final year of the war. Recognizing the importance of having fighters that could escort bombers all the way to their targets and back, the Luftwaffe's fighter control units endeavored to concentrate their forces at strategic points. The goal was to establish conditions where they could achieve local air superiority and counter the heavily guarded Allied bomber streams. This tactic, however, required meticulous coordination and precise timing, as dispersed German units had to gather at designated locations with sufficient warning to form effective, large-scale formations. These formations stood a better chance of challenging the bomber streams but faced numerous logistical challenges. Fuel shortages and communication breakdowns frequently hampered these efforts, even when German fighters managed to assemble and occupy advantageous positions. The presence of the well-protected P-51 escorts made any attempt to attack the bomber formations exceedingly costly in terms of losses. The strategic landscape had fundamentally shifted. What once might have been an effective tactic was now rendered significantly less so by the pervasive capabilities of Allied air power. This shift in tactical advantage was starkly evident by mid-1943, when unescorted or poorly protected bomber formations suffered devastating losses against well-organized enemy fighters and defenses. The situation worsened by mid-1944 when German fighters attempting to intercept the bombers faced an almost insurmountable obstacle, suffering catastrophic attrition against the robust escorting forces, primarily driven by the P-51 Mustang's dominance in the skies. After the war, the small, cylindrical drop tanks, designed to extend the operational range of fighters like the Mustang, became rare and highly coveted collector's items. Few of these tanks have survived intact to the present day, largely because most were destroyed upon impact or intentionally crushed by Allied ground crews post-attack, in an effort to prevent their reuse by enemy forces. The fact that these tanks were considered expendable meant they rarely held intrinsic value during wartime or in post-war recovery, making surviving examples quite scarce. Those few tanks that remain today have become treasured artifacts, displayed in museums and regarded as historical curiosities. For instance, the National Air and Space Museum in Washington, D.C., maintains several examples within its extensive collection, often displayed alongside the P-51 Mustang aircraft they were originally designed to augment. These tanks are noted for their construction, made from laminated craft paper soaked with phenolic resin, a material that provided the necessary durability while remaining lightweight. The manufacturing was carried out by companies such as Bowater Scott, and each tank's capacity was officially listed as being 108 U.S. gallons. Interestingly, the placards accompanying these exhibits tend to omit details about the intensive analysis undertaken by German engineers after the war. It is well documented that these experts spent weeks studying and examining the design and performance of the tanks, carefully calculating their implications and, through this process, gaining critical insights into the full scope of Allied industrial and technological superiority. This underlined not only the narrative preserved within a collection of technical reports and accounts from post-war interviews offers a revealing glimpse into the profound psychological effects experienced by German technical personnel during the conflict. These individuals were not merely analyzing a sophisticated weapon system. Rather, they were confronting a symbol of strategic resilience that transcended technological complexity. The so-called paper drop tank, which was not an advanced or cutting-edge invention, actually represented a deliberately simplified design, crafted using non-critical, inexpensive materials that could be produced rapidly and in enormous quantities. However, this simplicity was far more than an engineering choice. It served as a powerful message, one that spoke louder than any intricate technological feat could. It underscored the stark reality that the Allies possessed such immense industrial capacity that they prioritized optimizing designs for swift mass production over achieving maximum performance. The Allies had the ability to manufacture fuel tanks from paper because they possessed virtually unlimited supplies of paper, resin, and other raw materials, along with the necessary manufacturing infrastructure and an abundance of fuel to fill these tanks. This was not a matter of resource scarcity or desperation, but an explicit strategic decision driven by efficiency and industrial scale. German engineers who had years of experience in aircraft design understood immediately the implications of this approach. They recognized that they were fighting an adversary so affluent in resources and manufacturing capability that choosing to substitute materials or adopt simplified designs was motivated solely by considerations of efficiency rather than necessity. This realization played a crucial role in shaping their understanding of the shifting strategic landscape. In post-war interrogations with Luftwaffe personnel, this theme repeatedly emerged. When asked to pinpoint the moment they first realized Germany was destined to lose the war, many senior officers and technical staff identified the early spring of the year 1944 as a pivotal turning point. It was during this period that the arrival of long-range fighter escorts over Berlin marked a significant and decisive change in the strategic balance of power. Hermann Göring, who was interrogated after the war, openly acknowledged that the introduction of long-range fighters inflicted a substantial strategic blow to German defensive plans, a blow that played a crucial role in the eventual downfall of German air operations. Although the specific claim regarding Mustangs over Berlin remains unconfirmed by primary sources, Göring's post-war statements consistently recognized that Allied air superiority, made possible by long-range escort fighters, had been instrumental in Germany's defeat. These technical insights, gained by examining captured P-51 Mustangs and their associated drop tanks, contributed substantially to the advancement of aviation technology in the post-war era. Many German engineers, after the war, emigrated to the United States or collaborated with Allied military and technical intelligence agencies. Their detailed knowledge of American manufacturing processes and design philosophies deeply influenced their subsequent work. The emphasis on standardization, interchangeable parts, and designing for mass production became fundamental principles in the development of post-war aircraft. The concept of the paper drop tank itself evolved into a classic case study for wartime industrial innovation, highlighted in engineering schools and military staff colleges as an example of how resource optimization and large-scale manufacturing could confer a decisive strategic advantage. The P-51 Mustang, which became an icon of Allied air power, remained in service with various air forces well beyond the end of World War II. Its remarkable range and endurance allowed it to perform in diverse combat scenarios, notably during the Korean War, where it primarily served in ground attack and close air support missions. These attributes, initially celebrated for their role in escorting bombers across vast distances, continued to demonstrate their strategic value even in later conflicts, underscoring the lasting impact of that innovative design philosophy born out of wartime necessity. Europe proved to be an unexpectedly valuable theater for the P-51 Mustang, despite the stark differences in operating environments compared to its primary deployment areas. The aircraft's versatility and robust design allowed it to perform effectively in the challenging conditions of the Korean Peninsula, demonstrating its adaptability across diverse climate zones and combat scenarios. Remarkably, Some of these formidable fighters continued to serve on the front lines well into the early 1980s, a testament to the durability and soundness of the original design. The longevity of the P-51 in active service during this period highlights not only its technological robustness but also the enduring value it offered to various air forces around the world. Throughout the Second World War, the production of the Mustang exceeded 15,000 units, making it one of the most prolific American fighter aircraft of that tumultuous era. Its widespread use and critical role in aerial combat earned it a prominent place in aviation history. Today, more than 100 P-51s remain operational, preserved and maintained by dedicated collectors and museums across the globe. The sight of a Mustang soaring through the sky, often adorned with authentic wartime markings and insignia, serves as a poignant reminder of the aircraft's pivotal role in securing Allied air superiority over Europe. These flying relics continue to inspire awe, standing as living symbols of the technological and tactical advancements achieved during the war. The historical significance of the P-51 Mustang extends far beyond its immediate tactical or operational achievements. Its use of paper-drop tanks, which were deployed in large numbers during campaigns over Europe, encapsulates a broader narrative about industrial capacity and the economic dimensions of modern warfare. These tanks are emblematic of a conflict where industrial power was often the decisive factor, illustrating how warfare had evolved into a contest of production as much as combat. The outcome of World War II was heavily influenced by the extent to which nations could mobilize their industrial resources to produce vast quantities of weapons, ammunition, aircraft, vehicles, and supplies at an unprecedented scale. It became apparent that victory often hinged on the ability to sustain and outproduce the enemy, rather than solely on battlefield tactics. The United States, in particular, achieved a level of industrial mobilization that had no real precedent in history. At the peak of wartime production, approximately 1943 to 1944, American factories were churning out aircraft at rates surpassing 50,000 units each year. Shipbuilding was similarly prolific, with naval vessels being launched at a pace of multiple ships per day. Ammunition production soared into the billions of rounds, ensuring that American and Allied forces were consistently supplied for the relentless campaigns they faced. This extraordinary industrial effort not only supported American military operations but also supplied vast quantities of equipment and supplies to Britain, the Soviet Union, and other allies through the Lend-Lease program. Despite Germany's significant industrial capacity and advanced technical expertise, it was unable to match the sheer scale of Allied production. Germany's relative industrial shortcomings stemmed from several critical factors. Its manufacturing base was smaller and more geographically constrained, making it more vulnerable to strategic bombing campaigns targeted at factories and transportation hubs. As the war progressed, Germany also lost access to key raw materials as occupied territories fell into Allied hands. Resources had to be diverted to meet urgent military needs, often resulting in inefficiencies and reduced output. Organizational and logistical shortcomings further hampered Germany's war economy. Fundamentally, however, the most decisive disadvantage was that Germany was fighting a coalition whose combined industrial capacity far exceeded its own, an industrial disparity that proved insurmountable once the United States fully mobilized its vast economic resources in mid-war. The addition of American industrial might in 1942 and 1943 rendered the Axis powers' chances of victory increasingly slim, making defeat almost inevitable once full industrial mobilization was achieved. The symbolic weight of this industrial advantage was starkly illustrated by the paper-drop tanks that rained down over Germany during the final years of the war, 1944 and 1945. These simple yet powerful symbols of American industrial capacity served as visible proof of the overwhelming logistical and material superiority that the Allies possessed. Their widespread deployment underscored the profound impact of industrial scale on the outcome of the conflict, a message that was impossible to ignore. Throughout the war, German technical intelligence efforts were systematic and meticulous. Investigators and analysts carefully examined captured American equipment, maintaining detailed records of performance tests, material analyses, and technical evaluations. Facilities such as Recklin and others dedicated substantial resources to studying Allied hardware, often preserving comprehensive documentation that survived the turmoil of war in various archives. These records provide valuable insights into how each side perceived the technological capabilities of the other, and they shed light on the strengths and weaknesses identified during the conflict. German assessments of American equipment generally proved to be technically accurate. They correctly identified many of the design features, operational strengths, and limitations of U.S. aircraft and weapons. The careful analysis of captured American hardware contributed significantly to German understanding of Allied capabilities, informing their strategic and tactical decisions. These detailed evaluations underscore the importance of intelligence work and technical reconnaissance in shaping the broader dynamics of the Second World. The strengths and weaknesses of American aircraft, vehicles, and weapons during World War II reveal much about the nature of industrial warfare and the importance of production capacity in determining the outcome of conflicts between highly industrialized nations. While the United States developed exceptionally effective military hardware, the critical factor that ultimately tipped the scales was not merely the superior technology or tactical skill on the battlefield, but rather the sheer scale and efficiency of American industrial output. The ability to produce vast quantities of aircraft, vehicles, and equipment at a rapid pace allowed the Allies to sustain prolonged campaigns, overwhelm enemy defenses, and continuously adapt to the evolving demands of modern warfare. A prime example of America's technological prowess was the P-51 Mustang, a fighter aircraft renowned for its outstanding performance, agility, and range. Although individually a remarkably capable aircraft, the true power of the Mustang emerged when it was produced in enormous numbers, tens of thousands, in fact, which contributed significantly to establishing and maintaining air superiority across Europe. No amount of tactical ingenuity or technological innovation could have matched the strategic advantage provided by having such a vast and reliable fleet of fighters. This point underscores a fundamental lesson. Dominance in modern warfare is often achieved less through isolated technological breakthroughs and more through the capacity to mass-produce critical weaponry at scale. The story of German engineers examining paper-drop tanks at Recklin in March of 1944 offers a profound insight into the importance of industrial capability in wartime. Their focus on these simple yet innovative fuel tanks was a reflection of the broader reality that, in conflicts between industrialized nations, production capacity can be as decisive as battlefield prowess. The ability to manufacture more equipment faster, more efficiently, and with greater logistical support confers advantages that tactical and operational excellence alone cannot fully offset. Germany and Japan paid a heavy price for underestimating this lesson during World War II, a mistake that deeply influenced military planning in the subsequent Cold War era and continues to shape strategic thinking today. Maintaining the ability to produce advanced weapon systems, sustain supply chains even under intense stress, and train personnel more rapidly than they are lost in combat remains as vital now as it was in the mid-20th century. The capacity for sustained industrial effort can determine the duration and ultimate success of military campaigns, making manufacturing resilience and logistical efficiency core. Components of modern military strategy. The pivotal shift in the air war over Europe occurred in March of 1944 with the first missions to Berlin escorted all the way by single-engine fighters. This marked a decisive turning point. From that moment onward, no German target was beyond the reach of American bombers equipped with fighter escorts. The systematic Allied bombing campaign, although not without losses, became sustainable due to the ability to replace and repair aircraft swiftly, while continuously increasing operational tempo. Targets such as synthetic fuel plants, ball-bearing factories, aircraft manufacturing facilities, and transportation networks became recurring objectives, each attack further degrading Germany's war machinery. This relentless strategic bombing, combined with the Soviet advances from the east and the Allied pushes from the west and south, culminated in Germany's defeat roughly 14 months after the first P-51 Mustangs reached Berlin. Throughout this final phase of the conflict, paper-drop tanks proved instrumental in extending the operational range of American fighters. Production of these tanks persisted well into 1945, with thousands manufactured each month. These lightweight fuel tanks were not only used by P-51 Mustangs but also by P-47 Thunderbolts and P-38 Lightnings, effectively extending the reach of all American fighters engaged in long-range operations. British fighters, too, extensively employed paper tanks, especially for missions over occupied Europe and deep into Germany itself. The widespread adoption of paper-drop tanks exemplifies a broader pattern of resourcefulness and industrial efficiency that characterized Allied wartime efforts. Their production freed up aluminum and steel for other critical uses, such as aircraft construction and weapon manufacturing, while providing the crucial range extension necessary for strategic and interdiction missions. This careful matching of production methods to operational requirements, prioritizing efficiency over tradition, highlighted the industrial mindset that underpinned Allied success throughout the war. Today, military historians recognize that multiple interconnected factors, among them industrial capacity, logistical resilience, technological innovation, and tactical adaptability, were instrumental in shaping the outcome of the air war over Europe. The strategic use of mass production and logistical ingenuity not only allowed the Allies to maintain persistent pressure on German war industries but also laid the groundwork for modern concepts of industrial warfare and strategic mobility. In a combination of strategic superiority, technological innovation, and relentless operational effort, all of which contributed significantly to the eventual Allied victory in Europe. Over the course of the war, the Allies managed to establish numerical superiority in both aircraft and trained pilots, which proved crucial in gaining air dominance. They also held critical technological advantages in areas such as radar and advanced communication systems, enabling better coordination and situational awareness during combat missions. A vital component of the broader strategic campaign was the relentless aerial bombardment of German industry and infrastructure, aimed at crippling the Nazi war effort from the inside. This bombing campaign, combined with the sustained tempo of combat operations, gradually eroded German resources and manufacturing capacity more rapidly than they could be replenished. Such attrition was instrumental in weakening German defense capabilities, ultimately paving the way for Allied advances on the ground. Within this complex, multifaceted effort, the P-51 Mustang played a central role, especially thanks to its innovative use of external fuel tanks, commonly referred to as paper-drop tanks. These tanks, made from lightweight, glued paper designed for single use, significantly extended the aircraft's operational range. They became emblematic of the inventive spirit and resourcefulness that characterized wartime innovation. However, while drop tanks were important, they were merely one element among many. The victory in the air did not hinge on them alone but was the result of a collective effort involving various fighter aircraft, strategic bombers, industrial mass production, rigorous pilot training, intelligence breakthroughs, tactical innovations, and an unwavering dedication of resources over time. The paper drop tank, in particular, symbolizes more than just a practical solution. It epitomizes the American industrial ingenuity that underpinned Allied success. Technical files preserved at the Royal Canadian Intelligence SE Service and the German Bundesarchiv contain detailed documentation of American capabilities, meticulously recorded by engineers and technicians. These records include specifications, performance data, construction methods, and production estimates, reflecting the German perspective on Allied technology with German thoroughness and precision. Accessing these archives reveals that German engineers accurately understood many technical aspects of American aircraft and equipment, including the capabilities of devices like the paper drop tank. Despite this accurate technical knowledge, what they could not influence or change was the strategic and industrial realities that defined American strength. Recognizing an opponent's overwhelming technological and industrial advantages, as the Germans did, does not equate to being able to counteract them effectively. When disparities in industrial capacity, resource availability, and logistical infrastructure are so profound, military technology alone cannot bridge the gap. The enduring significance of the paper drop tank extends beyond its wartime application. It serves as a powerful reminder that effective solutions do not necessarily need to be complex or technically elaborate. A simple tank composed of glued paper, designed for a single mission, and manufactured from non-critical, readily available materials, proved to be an appropriate and efficient response to a specific operational challenge, extending the range of fighter aircraft. In this context, good enough was sufficient. The tank met its mission requirements without the need for unnecessary sophistication. This principle, developing solutions that are fit for purpose rather than pursuing technical perfection, has become a cornerstone of modern systems engineering. Oftentimes, the simplest solution that fulfills all necessary criteria can be produced in the required quantities and within the available time frame, is the most effective. The lesson learned from the use of paper drop tanks over Germany remains highly relevant today, whether in military hardware, civilian technology, or infrastructure development. The aircraft that carried these innovative tanks, the P-51 Mustang, stands as one of the most successful fighter aircraft in aviation history. Its legendary status stems from a combination of long-range capabilities, excellent performance, operational reliability, and ease of manufacture. These qualities made it an ideal escort fighter for the strategic bombing campaigns over Germany, helping to secure air superiority and protect Allied aircraft deep into enemy territory. The Mustang's success was not accidental but the result of deliberate design choices, technological advancements, and iterative improvements. It symbolized the effective integration of engineering simplicity with operational effectiveness. As a consequence, the P-51 Mustang played a pivotal role in the Allied victory, demonstrating how resourcefulness, strategic thinking, and practical engineering solutions can combine to achieve extraordinary results in warfare and beyond. The effectiveness of the P-51 Mustang during World War II was not attributable to a single innovation or feature. Rather, it stemmed from the harmonious integration of multiple critical elements, each contributing to its formidable performance in the skies. The design process, led by the talented engineering team at North American Aviation under the guidance of Edgar Schmood, resulted in an airframe that was aerodynamically optimized for high-speed, long-range flight. This meticulous design was complemented by the powerfully reliable Merlin engine, which provided the necessary thrust and endurance required for extended missions. Furthermore, the addition of a fuselage fuel tank significantly extended the aircraft's operational range, allowing fighters to escort Allied bombers deep into enemy territory. The availability of specialized drop tanks further increased this range, pushing the operational radius of the Mustang beyond the impressive threshold of 800 miles. These drop tanks, often made from paper and glued craft paper, became iconic symbols of wartime ingenuity, showcasing resourcefulness in the face of material shortages and strategic demands. It is crucial to understand that no single component alone rendered the Mustang such an effective weapon. Instead, it was the seamless integration and mastery over all these elements, combined with the industrial capacity to produce them at scale, that established the P-51 as the decisive escort fighter during the European theater of the war. This synergy of engineering, manufacturing, and strategic planning created a platform that could reliably perform over long distances, thus significantly impacting the air war's outcome. Reflecting on these historical developments, even after a span of roughly 80 years from the events of March of the year 1944, the lessons derived from these innovations remain profoundly instructive. When examining the captured German equipment at Recklin, engineers unveiled not merely technical specifications but also the underlying strategic realities of the conflict. The paper drop tanks, in particular, illustrated that the United States possessed an industrial capacity far surpassing that of Germany. American engineering prioritized pragmatic, effective solutions over the pursuit of technical perfection, exemplified by the rapid development and deployment of such innovative fuel storage methods. These insights demonstrated that the Allies had ample resources to optimize their aircraft and operational efficiency, rather than resorting to desperate or makeshift substitutions. Coming at a crucial moment in March of 1944, when the war's ultimate outcome remained uncertain but the tide was unmistakably turning, these revelations provided the German technical staff with a sobering understanding of their own limitations and the formidable industrial and technological gap they faced. This comprehension, however, could not alter the inevitable outcome of the war. Germany's defeat was predestined by factors beyond the reach of even the most skilled engineers working in testing facilities or military laboratories. Yet, the story of those engineers meticulously examining paper cylinders, crafted from glued paper, calculating fuel capacities, and noting their strategic implications, offers invaluable insight into how modern conflicts are often decided not just on the battlefield, but through industrial capacity and technological innovation. The conflict finally drew to a close in May of 1945, bringing an end to the most destructive war in human history. The systematic bombing campaigns, which heavily relied on long-range fighter escorts like the P-51 Mustang, equipped with those very drop tanks, played a pivotal role in crippling Germany's war machine. The combined effects of sustained aerial assaults, disrupted industrial production, shattered transportation networks, and depleted fuel supplies gradually rendered the German war effort untenable. The Luftwaffe was reduced from a formidable fighting force to a mere token presence, incapable of mounting effective resistance. These outcomes were the result of a complex interplay of numerous factors operating over several years. Yet, central to the Allied success was the ability of fighters like the P-51, armed with drop tanks, including some constructed from paper, to escort bombers with unwavering reliability across vast distances. This capability was arguably one of the most decisive elements shaping the final stages of the conflict. The paper drop tanks themselves, many of which have survived and found their way into museums, serve as enduring artifacts of wartime ingenuity. Their true significance, however, transcends their physical form. They symbolize the strategic application of industrial capacity, technological ingenuity, and resourcefulness in solving pressing wartime problems. These tanks epitomize how modern warfare is ultimately won through the mobilization of overwhelming production capabilities, where innovation and strategic purpose go hand in hand. The historical importance of these objects and the technical reports from Recklin and other archives continues to resonate today, offering vital insights into the nature of World War II and the crucial role played by industrial capacity in determining the outcome of global conflicts. Their story reminds us that victory in modern warfare often hinges less on individual technological breakthroughs and more on the ability to produce and deploy vast quantities of effective, well-integrated equipment, an enduring lesson from one of history's most pivotal eras.